So today I want to sort of start with a little summary of what we're trying to do. So I started with the TASEP on half space in full generality. So you have forward and backward hopping and in and output at the boundary, general boundaries. And what we compute was the, well, we analyzed this using vertex model approach. So I had this G U mu, which was the sort of discrete six vertex model with open boundaries. And then there was some continuous time limit that this would go to the TASEP, well, some presumably continuous time limit to the TASEP transition probability. So we have this object in full generality, and then you can, in principle, take this limit, although in some cases, in the full general case, this is still a little bit tricky to take. And then I sort of focused on TASEP, so Q to 0, and also the output rate on the left boundary to 0, and that would simplify this formula quite a bit, and we could take this limit here. And we saw that this then led to a Pfaffian or the transition probability to go from some, say, initial state to a final state for a large class of initial conditions. And I particularly looked a lot at the empty initial state. And so what I started doing then, and what I'll focus on today, is to reformulate this as a conditional Pfaffian point process. Because even though this is a Pfaffian expression, it's still not really easily amenable for asymptotic analysis, for example. So what we want to do is reformulate it as a Pfaffian point process on the Kelvin-Zetland patterns, and then using results of Bardeen rings. And as Leo remarked, this is sort of a not meta or Pfaffian's theorem to express the correlations of TASEP as in terms of Pfaffians using this correspondence. So that is sort of the overview.
Can you remind me what there was some funny condition on mu for which this worked?
Yeah, so if the number of particles in the final condition is n, then mu I should be larger than n minus I.
Or empty. No, the empty doesn't work for the empty state, right?
No, this is a good point. Yeah, or empty. Somehow this is special here.
And is there some sort of
basically it needs to be empty close to the boundary.
Sorry, what?
It needs to be empty close to the boundary.
Oh, I see. But is there some physical reason for that, or you just don't understand the other cases?
We don't understand the other cases.
But
well, presumably there's also a physical reason. There's some stronger interaction with the boundary than in this case.
I see. Okay, maybe some kind of spatial phase transition. Who knows?
Who knows?
Oh, I mean, it's interesting.
It's definitely interesting. Yeah, no, I don't know the answer to that. Okay, so today I'll focus on these last 2 points a bit. So maybe I'll recall again that this transition probability from empty to new was given as sum over triangular arrays of some measure on these triangular arrays. This measure was given by some determinant of like indicator functions. Like this, where zi to the k was equal to nu k, the physical coordinates. And the z's belong to a triangular array. And then we had some virtual coordinates that we needed, which you can think of as labeled infinities, but we needed them to sort of frame this this formula. And so the claim is that this measure defines a conditional Pfaffian L ensemble. And so I'm going to be a little bit more precise about that. So this is not really my area, this L ensemble. So
do you just mean point process? What's an L ensemble?
Yeah, so this is going to be the definition. And yeah. So I'm going to think of Z is a set of points. And L from Z plus Z to see 2 cross 2 is like is a 2 by 2 matrix valued function. And then so a measure on Q to the Z is a so I'm taking this from borrowed in range. If mu of x is the Pfaffian of L restricted to x and then normalized for any subset of Z, set of points, and this J of x, y taken 2 points is this 2 by 2 matrix x, y. So for those of you who've worked with half space models will be very used to this. So when you deal with Pfaffians, say everything that is identity in the determinant case gets replaced by a J in the Pfaffian case. So one way of thinking, and everything will be expressed in terms of 2 by 2 blocks, because we need to sort of take Pfaffian and make sure that the dimensions of all sort of matrices are even. And then it's a result of this paper which is the analog of A naught meta, that the correlation kernel is given by K equals J plus Jx plus L inverse restricted to the subset that you're looking at. Right. So any correlation function you want to measure on this process can be expressed as a Fredholm Pfaffian with this kernel. And this is the result I want to use now for TASEP, because we can express TASEP as a sum over these Pfaffian point process. And that means that ultimately some correlation functions in TASEP, or all of them, should be able to be expressed in terms of potentially sums over Pfaffians with this kernel, or like a Fredholm Pfaffian with some projectors in it. So what we need to do really is to compute this inverse. And I want to sort of talk about it, how to do that a little bit today. And this is sort of a little bit involved, unfortunately. But yeah, that's.
By correlation kernel here, you mean, what is the meaning of X? Are you restricting to indices in X?
Oh, well, it'll become clear. So
you're writing K of X on the left on this proposition.
So I'll be more precise. Yeah. So let me be more precise and describe this L ensemble for empty initial conditions. So I'm going to take X as this set, and B as the well, we're going to use daggers. So I think Daniel liked this notation of daggers for the virtual coordinates, because they're really like sticks in the ground and they're there forever. So these are the virtual coordinates. And we're going to think of tilde x as the union of the virtual coordinates with the physical space. And then the triangular array but I call lambda is the set of points ixj in X, where I runs from 1 to n, and j from 1 to I. So this is really the picture that I showed yesterday of the Gelfand-Settling patterns, and the values that x can take value in natural numbers. Okay, so then this W and Z, this measure that we got from TASEP, was a measure on these triangular arrays, and it can be extended to so to X. So it's a conditional Pfaffian ensemble on X as a seen as a subset of this x twiddle, so the extension to the virtual coordinates. But we really want to measure on the physical coordinates. We just need those vertical coordinates to be able to formulate everything. Okay, so let me define this this function L. So this W is now going to be the Pfaffian of L. So thinking of L going from the two copies of the full space to a matrix value 2 by 2 matrix value 2 by 2 matrix. And so I need to describe to you what it does. So on the virtual coordinates, this L is going to be basically this J. And between a vertical coordinate and a physical coordinate on the triangular pattern, or the triangular array, this is going to be some indicator function. And if I sort of exchange, then it's just a transpose of that. Just to make the 2 by 2 matrix that I get will have to be anti-symmetric. So, and then on the between a pair of vertical coordinates in my triangular array, or sorry, the physical coordinates in my triangular array, this will be the psi function that we got from TASEP. Maybe I should. So this transition probability from empty to new was the sum over Z in Gelfand-Seton patterns written by you, Pfaffian of this psi. Z I to the n, Z j to the n. Right, that was the function psi. So that psi appears here in the last block. And then there are off-diagonal indicator functions like this. Okay. And so the dilemma is that I'll write this out in a more visually appealing form. Dilemma is that for a subset A of a triangular array, the Pfaffian of this L restricted to the virtual coordinates union A is the measure W on A if A is a triangular array and 0 otherwise. So taking a subset of that triangular array, then the Pfaffian of this matrix will give us that measure W if A is a physical set on the triangular array, 0 otherwise. So I'm just trying to set things up in a way that I can use this proposition here. So what I need to do now is, well, to you, I just wrapped it up. What I need to compute is really something like J of X plus L inverse restricted to the physical space. So I need to separate out all the virtual coordinates from the physical coordinates, and then look at Jx plus L on that physical subspace. So let me try and write L. So the explicit form of L on well, so I just need to order my space. So what I'm going to define is Zk as the set of points Z1, K, all the way up to Zkk. So if you like, it's one of the fibers in my triangular array. And I'm going to need 2 copies of those to write my Pfaffian as 2 by 2 blocks. So I'm going to think of Zk prime and Zk double prime as 2 independent copies. And I'm going to then write L on the union of 2 copies of my vertical coordinates, V prime and V, union with the first fiber, and then well, a copy of the first fiber and another copy of the first fiber, and so on until we get 2 copies of the last fiber. So then this L will look like following. There's going to be a top element, which is just going to describe the interaction between the. So this is really like n by n block of 2 by 2 matrices that describe the connection between the virtual coordinates, right? So that UN sits in this block, 2 copies, and then we get some structure like this. And sort of only in the, hang on, then I get 0, 0, 0, 0, W1. Finally, my psi sits over here. So my claim is this is L. And so really think of this as in 2 by 2 blocks on where the columns and rows are labeled by these spaces. So the physical space, what I'm actually interested in is this psi that sits here in the corner. Everything else is like indicator functions and projectors, so that I go to the right space. So right. So maybe I should say that this these e's of k minus 1 really are like by the indicator of the virtual coordinates with one of the physical coordinates, and w k are well, is it k? Is it k plus 1? Right. So w, one of these w's that appear here on the off diagonal, I take one z out of one copy of zk and another copy, and that really represents this indicator function. Okay. Okay. So now what we need to do is take L restricted to my subspace X. So get rid of the virtual coordinates, add J to it, and then compute the inverse of that. So if I want to add Jx to this, I'm going to just have to do it in the right way.
Over by 1.
Okay.
That's fine.
So there'll be these J's on the right column, rows and columns of the matrix, including in this last block here. So this is Jx plus L when restricted to X cross X, and I need to compute the inverse of this matrix. Did you have a question?
No, it's fine.
Okay, so then there's a little lemma. If you have a matrix of this form, which is sort of this form, and you need to compute the inverse of this, assuming that well, so my A matrix sits here. This is B. This is minus B transpose, and this is D. So I'm assuming that this matrix is invertible, which it is. So this is assuming that D inverse exists. This is equal to some matrix inverse, D inverse BT inverse minus M inverse B. So this is a little lemma that, so these are all matrices, assuming the inverse of D exists, and the inverse of this 2 by 2 matrix is given by this 2 by 2 matrix inverse. And I really only use the fact that D is invertible and this M is also invertible, which are very mild assumptions. So then it's a little lemma. So the first thing to compute is really this D inverse. So D is this block here, and we need to compute the inverse of that. And the inverse is given by this is why. So I need to tell you a few things. So this phi KL XY is a convolution of phi K up to phi L minus 1 XY. K is less than L, and it's an indicator K is equal to L, and 0 K is less than L. And what is this convolution? It just, so F star G XY is the sum over nu large equal 1 F of X nu G nu Y. So it's like it's an inner product, but sort of in the infinite index. So I'm claiming, oh sorry, and then I need to define psi. So psi of ij n is phi I up to n star psi star I j up to n. Transpose. Okay, so we have to convolve this this function psi that we sort of started with in the lecture 1 with these indicator functions, or these extended indicator functions to get an object that appears here. It's sort of a, I know this looks fairly intimidating, but it's actually a nice exercise to show that that's the inverse of this block. If you do that by hand, sort of you understand the sort of how this works actually. And it's, even though this looks intimidating, I have to say that I sort of enjoy doing that. I don't know who else did it, but I thought it was a, it's actually not so hard, but it's a nice structure to see how it works.
Sorry, that big block.
This big block here. Oh, so then, yeah, this is, so this, yeah, so this is like D.
Including 1 minus 1.
Including 1 minus 1.
Anything else in there is zeros? I mean, is it tridiagonal D?
Yeah.
Including the last row and column?
No. Yeah, except for the last two elements. Yeah.
So the inverse of the tridiagonal, it's not that complicated.
Sorry?
I mean, you could say the inverse of a tridiagonal matrix is not that complicated. It has some recursive structure, which is what you're describing here.
Yeah.
Okay.
Yeah. So, I mean, maybe this is a comment for the experts. All through this talk, all my matrices are finite dimensional in terms of the number of particles in the system, this n. And in particular, it means that this psi here, which is the convolution of the original psi, which is not dependent on n, like the TASEP transition probability was the Pfaffian of this psi, if I take the Pfaffian of n by n size, but in principle, the matrix elements don't depend on n. I could take a larger Pfaffian. But because I need to do this convolution in this sort of setup, I create an n dependence because all these indicators depend on n. They sort of truncate there. So all the formulas implicitly depend on n in this way. And so we always sort of work with conditional probabilities that the number of particles in a system is n, and then we can compute correlation functions conditioned on that property. Um, so, sorry, what do I lied a little bit, right? This was not D, this was JX plus L, so JX plus D. So the minus 1 1 is the JX. D is the thing without the JX. And then we need to know this is the inverse. The inverse of this is this expression here. So we have D inverse and we also need to compute this. This is sort of the hard part. As I said, D inverse is not so hard. It's given here, but we need to know this, which includes n. Okay, so then you can you can sort of write this out formally, and what we then find is that JX plus L inverse restricted to the physical space, so to points in my triangular array, so not the virtual coordinates, is given by sum over K and L 1 to n psi I K minus 1 n So M is going to be this matrix, or M inverse, the inverse of that matrix. And I'm claiming that this expression here can be written in this form, where this psi ikn was the object defined here that I explained, depends implicitly on n. And it takes as entries physical coordinates and virtual coordinates, but the virtual coordinates are summed out against this, this matrix M, which is just a scalar matrix between the virtual coordinates. And these are again indicator functions, and then this is just a row vector with the same quantities there. So we need to compute this. Which is still hard. In particular because the inverse of this matrix is very difficult to compute. So we really don't want to do that. And so there's this trick to change basis and go to a basis where this M is diagonal, and really where M is given by J, essentially. Right, so we're going to choose a convenient basis. So how do you do that? So we can, because M is a anti-symmetric matrix, we can decompose it. We can decompose M inverse as minus R inverse transpose JR, where R is some upper triangular matrix. But this is a standard result for just any antisymmetric matrix can be written in this way. And then we want to change basis. So what do we want to do? So this M inverse is going to be replaced by this R minus transpose JR. So think of there being an R here that is then going to act on these expressions here. And if we then look at this psi, what is psi? It is this phi in times psi without indices to phi. So really what I'm going to get here is some R times phi, RKL times phi L minus 1n star psi. Right? This is going to be present. Hope everyone, can you see that or not? Should I will be more explicit? So M inverse sum over L, KL, psi L minus 1 J. So really focusing on this bit here now is going to be minus R minus T J R psi. Yeah, I was just struggling with the indices. So really you want to think of this as AL psi of L minus 1. Well, and this psi is going to be this. So I have phi of L minus 1 and star psi star the rest. Okay, so I really want to pull this bit. So R contains the information about M inverse that I don't want to compute. And so I really want to call this bit something new. So let's call this one phi. So on, I've just, yeah. I'm going to call this a phi n minus kn of x is going to be sum L is 1 to n R KL. This R depends on n star phi L minus 1. Like that. So you do this basis transformation. And that sort of magically gets rid of this M inverse, but of course it then remains hidden in this phi. But if we use phi, the expressions become a bit nicer. So now this kx plus L inverse on x plus x on a pair of physical coordinates is going to be I of in. Okay, so one thing I now need to do is that whereas this psi of Lj had a phi that runs from L minus 1 to n, and n was sort of a special, I mean, this is fixed for the whole thing. So what I now also need to do is compute the action of R on phi of L minus 1j, but j runs from 1 to n. So it's not obvious, but if I have this basis, if my sum, if I have a phi L minus 1j, what that is in terms of these phis. So what we need to do is somehow compute the sort of an inverse phi. So I'm going to claim there is something called phi of minus in, such that phi of ij is equal to phi of minus in by jn. Probably it should be the other way around. So jn by minus in. So I can replace this L minus 1j with an L minus 1n times sort of the inverse, going back to I. And then this R, the R that comes from this M now acts on phi I L minus 1n here and also there. At the cost of having to introduce these minus signs, which you can do. So they appear here. So we finally get sort of to this expression. So the psi and the phi are all explicit. We've just moved to a basis phi where if we knew phi, then we could just easily compute this. And how to determine phi? So phi is so phi k and solves is q by orthogonalization. Jijn is minus phi and minus I psi and like this. And just to remind you again that this psi was the original psi that appeared in the TASEP transition probability. So it's the thing that we needed to take the Pfaffian of to compute the TASEP transition probability. And if you're with me still from the first lecture, this was equal to what I call Q11. The n by n matrix Q11. So what we need to do now is solve this bi-orthogonalization problem, which actually is very hard. So after all of this, but I mean, this is a standard process. So for the full line, you follow a very similar process, except the technicalities are a lot easier, because here so everything is doubled up somehow. And you can solve the bi-orthogonalization process. But I just want to essentially leave it here, that given a solution of that, the correlation kernel Kij can be written as Kij11, J12, like that, where these Kij's now are given in terms of these of the inverse of this matrix, so in terms of these expressions. So for example, K11 would be this original function psi minus like something like sum n equals a. Sorry, A0 to n over 2 psi in star phi 2a psi an star minus, and basically this is like a interchanging the odd and even indices. So again, those who've worked on Pfaffian Gier process or Pfaffian processes would sort of recognize this structure, hopefully. So the structure is there, and it's really now solving this Q by orthogonalization process, which you have to do in this case to get. But these size of these phi's will be very similar looking to the original size. So it'll be like double integrals that you would get. Okay, so just as a final comment, once you have this correlation kernel, you can now, in principle, answer any sort of question on TASEP correlation functions and express it in terms of a Fredholm Pfaffian of this type, like J plus K, and maybe we'll put some projectors here. So the type of correlation function you want to compute will determine some sort of projector on particular particle configurations. So you fix your points using these, and then computing this will give you the correlation function using this kernel. Okay, so that is sort of the process, and then you can, well, do some scaling. So this is the calculation for empty initial condition. As I said, we can generalize this to more general initial conditions, as long as that first bit is empty, as long as we don't put the initial condition not too close to the boundary. But that will hopefully then gives us some sort of amenable expression for asymptotic analysis when you have those initial conditions. Okay, so I think that's the last thing I want to say. So thanks very much for listening. Yeah.
Questions for you?
So does the other initial condition only affect the particulization problem like in TASEP, or is it something else?
Yeah, so this corner that I had here, that will now involve some these functions psi that I had earlier. So these now get involved. So they enter into this the inverse here. So so let's see. I don't think they actually enter in they enter in a fundamental way in this Q by orthogonalization. That would just enter really here at this site. So for those initial conditions that are compatible with this setup. Yeah.
Questions?
I think you mentioned that the ensemble that you began with is not actually a probability. Like on the maybe Gelfand patterns, this is some probabilities are negative or something like that. Can you remind me something?
Yeah. So in some cases, the measure on these Gelfand patterns is not necessarily positive. Oh, but the formalism and the algebra still works through. And so this Gelfand business is like some auxiliary process that has not really physical meaning in terms of TASEP. You just use it as a tool to compute things.
And at the end, the Pfaffians that you have for the correlation kernel, you know that they give something positive because it comes from the TASEP.
Yeah. Yeah.
I see. And can you do multiple time? This was for one fixed time. Right?
This is fixed time, yeah.
Times is much more.
Uh,
But in theory, is it the same or?
I don't know. I don't know if there are experts on the full line case, but even there, I don't think you can do multiple times. So I guess we hope that it could be extended to that sort of case, but the starting formula was already fixed time. So you would. This is not inconceivable that you could write down some Pfaffian expression for the. No, actually, you can't. You write already sort of a. The transition probability from time 0 to time t, right? So that's already sort of between two different times, if you like. So I guess in principle you could address questions like that.
But already for the full line, it's a problem. I can write it down. Correlations which can done several times.
Is it possible?
Yeah, I think so.
That has been done, or?
No, I mean, if even for the full line, I mean, if you try to write down, explicit formulas for correlations at 3 different times, I mean, I don't think people know how to do that, right?
No, 2 times, yes.
No, 2 times, well. Yes, they must see, yeah.
I guess there's for TASEP, because of this sort of
Yeah.
structure, there's some hope. But you see already. I've punished you in 3 lectures with all this stuff. How hard it is to actually. And yeah, we just talking with BL that you're right. Every detail has to be correct. It's quite. But the structure is quite tricky.
Any further questions? Yeah, let's thank you.